we are going to vacuum filtrate, or we separate the crystals using vacuum filtration. So while this is taking place, I'm going to prepare my vacuum filtration apparatus. Okay. I want to also repeat how to use vacuum filtration. Anytime you want to keep the solid, when you have a mixture of solid and liquid, and you want to keep the solid, you would use vacuum filtration. When you have a mixture of solid and liquid and you want to keep the liquid, you would use gravity filtration, because you want like clean liquid only. You don't want to force anything. When you are keeping the solid, you want to force the liquid to be removed as much as possible. And then you want to wash the crystals with the solvent that you have, with the cold solvent of what you have in this mixture. Because this was an acid-base reaction and the solution is an aqueous solution, so we have water as the solvent. I'm going to make some ice, prepare some ice water. So I have the cold water, placing in ice to get to have it ready. So I'm just using the time to make this ice water ready when I'm about to wash the crystals. The way the vacuum apparatus, this setup, at least it works, because it can work also with the water aspirator, but we do have vacuum pump downstairs. We just turn on the vacuum and it operates here. I want you to pay attention to this piece that it's necessary, is called a trap. And what trap does, in case you are not paying attention and too much of the liquid as a filter has been accumulated here, the vacuum is going to pull that liquid and it could send it to the vacuum pump. And of course, water and electrical devices is not going to be very, working together good. So it's going to burn the pump. So we put this trap. So in case any liquid goes into to this tube, the vacuum tube, it would be trapped in this container. The way it works, I'm going to filter my sample into a filter paper because the Buchner funnel has large openings. So I cannot filter the sample directly on the Buchner funnel. I'm going to use a filter paper, properly cut size of the filter paper that covers all of these openings. Since I'm going to collect the sample on this paper, then dry it and weigh the sample, I need to have the mass of the filter paper. And since I'm going to keep it on the watch glass, so I'm going to get the mass of the combined watch glass with the filter paper and then put the samples on it later. So let's record the mass of the watch glass with the filter paper using the scale that was paired already. Making sure that it's paired and it only shows the number so now you're going to use the scale, make sure it's paired so it doesn't show any mass, it's 0. Place the watch glass with the filter paper. As soon as it's stabilized, we are going to record that number. Now we have the mass of the filter paper. We place this pre-weighted filter paper in the Buchner funnel, add a few drops of preferred cold solvent, add a few drops of water in this case, because our solvent or washing solution is going to be the water. Then transfer the mixture in order to transfer the mixture into the Buchner funnel, I make sure the vacuum is on. So I turn on the vacuum. So now if you can hear this fizzing sound, means that the vacuum is on. I'm going to mix this mixture because I want to get all the solids into the filtered paper and vacuum. If you can hear that sound is coming from applying the vacuum. Some crystals are left in the beaker. To transfer the crystals, I'm going to use cold solvent. Not too much of cold solvent and not room temperature of the solvent. Neither one of those are healthy because it would redissolve the sample. And I would transfer everything that is left in the beaker. Even if it takes like 2 times washing, I would do that. Transfer all the crystals with minimum amount of the solvent into the Buchner funnel. For effective washing of the crystals, because these crystals need to be washed now, I would turn off the vacuum, add cold solvent, and again, must be cold solvent so it does not redissolve. I pour the solvent over the crystals. Okay. Get the crystals soaked into the solvent, turn on the vacuum. Now, the crystals are washed. I'm going to continue applying vacuum for about 5 minutes to get as much possible of the moisture of the water out of these crystals. After the 5 minutes, I transfer that into the watch glass that is also weighted, pre-weighed. 2 options, leaving overnight to dry or leaving in the oven with the temperature setting of 102, because the literature value for melting point of the acid is about 120. So the boiling point of the solvent that I washed last is 100 degrees Celsius. So I'm setting up at 102. And I will leave it there for a few minutes until it's dry. Air drying, however, if there is opportunity for air drying is going to work the best, because we are avoiding any possibility for melting of the sample inside the oven. After the 5 minutes, extra 5 minutes of vacuuming or applying vacuum, now I can transfer the solid into the watch glass. You can just flip it just like you would remove the cake or transfer the cake, or use a spatula and remove the crystals with the filtered paper and place it on the watch glass. Now we have the crystals. We have the crystals we are going to leave it in the oven to dry. The sample in the oven and for about 5 minutes for it to dry. And while this sample is drying, we're just trying to be efficient. We are going to go and look at our ether solution. If the ether has evaporated completely, we can measure the melting point and mass of the sample and the melting point. Okay, we're just going to take the time about 5 minutes, or we are going to heat up until it's dry. Okay, back to the field where we had the sample with the ether. Now, dry. The ether has evaporated. That was nice. Dry the outside of outside of the beaker because of the evaporation, the outside sweats, and is moist. Dry the sample, the outside, then measure the sample. Now, this is the sample of the beaker with the label. We have the empty container. Now, with the neutral compound. So taking an image for you, taking a picture of this to post it for you, and you can report this mass. Next step would be to measure, to prepare our sample and measure the melting point of the sample. This sample is also going to be saved for next experiment, which is chromatography. I'm using the sample that we separate today. So I would save it for melting point and for the next experiment. You don't need the chromatography result to write a lab report for this experiment. I'm just saying I'm not getting new sample, just using this sample for one part of next experiment. Okay, get ready for the melting point. Okay. This sample must be dry. If the sample is not dry, it would be hard for it to get into the capillary tube, or it can get into capillary tube, but you won't be able to transfer it down when you're dropping through the hollow glass tube. So if it's not dry, what would you do? You're going to prepare a hot water bath at 60 degrees, which is higher temperature than boiling point of ether. We place in the hot water bath until it's completely dry. The sample looks very dry, and we are going to measure the melting point, and that would be the moment of truth, because if the sample is not dry, it would melt very, very quickly. So I'm going to add some of that on the main paper, and because it's shiny, it's easy to crush the sample in here. We don't have to bring the mortar, and it's finely powdered. So very easy now, because it's dry, easily it's going into the capillary tube, and I will drop it through the hollow glass tube. You're all pro on measuring melting point now, so you know all the steps. I'm just trying to get it done and show you also that I am measuring as I'm measuring the melting point for this sample. Capillary tube, place it in sample holder, and I use the same thermometer that I have calibrated last time. I'm using the same thermometer. The melting point of a pure sample of our neutral compound, which because it's fluorine, is about 110. And the setting based on the chart that we did talk about first class is going to be around 410. We turn it on and wait for the sample to melt and record the temperature. I would record the initial melting when I see the droplets of the liquid in bulk of the sample, and the final temperature for melting when the entire sample is melted, or as soon as the entire sample is melted. So I'm going to stop the recording at this point and get the, pay attention to the melting, but I will take a picture of the temperatures that for initial and final melting for you to record that number as initial and final, so you can use for your lab report. Okay, it has been 5 minutes for this sample or more, and it's just turning to the left side, the oven will open, and it's remove the sample from the oven. It's hot, so I would use either hot glove, or for small samples, I can use a tongue to remove it. And to close the oven. Now, is this sample dry? I usually tell the students, if the paper is dry, the sample is dry. And if I move this around now, I can show you that this paper is crisp. Okay. This paper is crisp. It's not wet. See, if it's wet, it would fold, and you could see. It's hard to feel it from the video. Of course, either you can trust me or you can see the texture. This paper is dry. And since it's dry, it kind of is telling me that the sample is dry. By the time I take it to the scale, it's going to cool off also, because we should never weigh the objects that they are hot. And after we measure the mass, we prepare the sample for melting point, and we measure the melting point of this benzoic acid as well. Okay, we are going to measure the mass. The object has reached the room temperature. The best scenario, it would be if you have a hot object, you place it like in a desiccator that doesn't have any moisture for it to be absorbed by the object. So when you measure it, it's actually dry object. And if we don't have desiccator or readily available desiccator to use it every day in the lab, we at least have to be consistent at the temperature that we are measuring the mass. Because I measure the mass of the filter paper and the watch glass at room temperature, this has to do as a hot object is cooling. One idea, at least, as the object is cooling down, it can absorb some moisture from the air. But if you are consistent in the temperature before and after, it should cancel any of the error. Now we have the object. Let's measure the mass and record the mass. Or for you, are going to watch the video for the picture that I will post for you to get the mass. Okay, we have the mass of watch glass, filter paper, plus 12 crystals of organic acid. We had the empty container. When you subtract, you get the mass of the recovered organic acid, which in this case is the benzoic acid. We started with like 0.5 gram. Now, if you get this mass, you divide by 0.5 or the number that you have reported, exact number, and times 100, that would give you the percent recovery of this sample. Same thing for the neutral compound. When you find the actual mass of recovered neutral compound, you are going to record that mass as the recovered neutral compound, divide by the initial mass that you started with, which was about 0.5, times 100 to get the mass of or percent recovery of the neutral compound. And I'm going to measure the melting point of the benzoic acid and post the pictures of initial melting, final melting as well. You already know how to prepare the sample. You already know how to measure the melting point. You don't have to watch that part of the video. So the video would be paused during the melting. You would see the numbers. The data you have, the collected data you have from this experiment is the mass recovered for neutral compound, mass recovered from the organic acid. You have the melting point for the organic acid, and you have melting point for the neutral compound. Now, the mass that is recovered, or percent recovery of each mass, it can tell you like how efficient you work and how much of the sample you have lost during the process, or if the extraction method was efficient enough to give proper percent recovery for each of the samples separately. The melting point, it can tell you if the sample is pure or how pure the sample is, which you are going to use the melting range of the sample. If it's wide range, anything higher than like 2 degrees is considered high range of the melting. 2 to 3 degrees is going to be high range of melting, and high range of melting or wide range of melting indicates that sample is not completely pure. So which you can write about it, you can explain what you think happened, that the sample is not completely pure, maybe it's not dry completely, or other factors. And if the melting point is close to the literature value, you have pure sample. That means your extraction was done properly and the extraction method is effective. Thank you. That's the end of this experiment. Just need to collect your data. Thank you.